Hey, grade 8, we are continuing on our discussion of simple machines by talking about wheel and axle, gears, and pulleys. So to start off, we're going to talk about the wheel and axle and how that works. And really what the wheel and axle is a modified form of a lever. So if you had a lever, okay, where this is like your fulcrum, yes, and then this is, your load arm and your effort arm. Well, all that's happened here is that when I have a wheel and axle, imagine that this part where the fulcrum is, that's just been kind of like moved out. So then the lever continues here instead of here. So hard to show in 3 dimensions, but this is going into the page and then the lever continues. So if I take a look at this diagram, it's kind of like this is one of the arms. Here's the fulcrum. And then over here is the rest of the arm of the lever, okay, from here to the edge. So it's essentially just a lever that's made out of 2 circle things. So wheel and axle combinations come in many different forms, and definition of wheel and axle, it's a combination of 2 wheels of different diameters that turn together. It's a lever essentially that rotates in a circle around a center point or fulcrum. So all the time what I've got is just essentially a lever, but it's a continuous lever. So here I'm drawing the lever as here's one arm and here's the other arm. Well, instead I could draw it like this. Here's one arm and then here's the other arm, right? The continuation of that, with this being the fulcrum middle point. But it's just a lever in the form of 2 wheels that are connected, rotating on the same axle. A great example of a wheel and axle is a winch. And a winch consists of a small cylinder that has a crank or handle, which is essentially a larger cylinder, which looks more like a lever, right? But with the winch, here is your effort arm right here. And then this from the center to where the inside of that wheel is, that the cord is going around, well, that's your load arm. So if you look at this, this would give a force advantage, right? If we were looking at this as a lever, because you have this large effort arm and then this tiny load arm. So this would be equivalent to a lever like this, where this is your fulcrum and this is your load, or your effort arm, and here's your load arm. So this would give a force advantage, so you don't have to apply as much effort here in order to lift the load here. Well, same thing when I'm taking a look at this wheel and axle. I can apply the force on the handle here, on the effort arm, and then that allows me to have a force multiplier, a force advantage, in order to actually pull in the thing with the winch. So it's a lever, it's a special lever. By exerting a force on the handle to turn the wheel, the cable will then pull back the load. And you can use winches to, pull cars and stuff. And it's because you're getting this amazing force advantage from the design by having a larger wheel, essentially. That's the handle lever, or the handle. And then the smaller wheel that the cord goes around. So here's a diagram of a winch for pulling up a boat. We can agree that pulling up a boat would be tough, but with the winch, it's not as bad. And this is giving you a force multiplier or a force advantage, because here you have essentially the load arm, and then from here to here you have the effort arm. So it's just acting like a lever. But with the rope, it ends up continuing on and on and on forever as we turn that. So to calculate the mechanical advantage of a wheel and axle, all we need to do is use the lever formula, because it essentially is a lever. And we just have to take a look at the effort arm and divide it by the load arm, the same way as we did for a lever. So what is the effort arm? Well, the effort arm is the thing that we're putting the force on. So when it came to the winch, the effort arm was what the person was actually turning, yes? While the load arm was the smaller kind of axle or whatever that the cord was going around. Same thing, with anything we're looking at, the effort arm is what the person is applying the force to, and then the load arm is, lifting or doing something to something else. So yeah, and that really is how we can calculate any mechanical advantage that we get from a wheel and axis combination. And we're looking at the radius. So again, that is from the center of the wheel to the edge of the wheel. We're comparing the radius of the two things. So if I was looking at this particular system, I've got the radius of the actual axle here, right? Let's call that little r. And then I have my radius of the wheel. Let's call that big R. Now, let's say that in this example, the force was actually being applied, the effort, to the axle. So the axle was turning, and then as a result, the wheel turned. Well, in that kind of case, my effort arm would be the little r, the small radius, and the load arm would be big R. So what would happen here is that this would be a speed advantage instead of a force advantage, because I'd get a value much lower than 1. But we'll do examples, we'll take a look at stuff later on. A great example of a wheel of axle is a screwdriver even. When you think about a screwdriver, this is essentially your axle, and then the screwdriver handle is your wheel. And this gives you a force advantage. And the reason why is because the radius from here to the outside is much bigger than when we look at the screwdriver, the radius from here to the outside of the shaft of the screwdriver. So this is giving us a big force advantage because we turn the handle, and then as a result, it causes this to turn as well. Okay, so if we actually wanted to figure out for a screwdriver what we had in terms of a advantage, we could take a look at the handle, yeah, and we could figure out the radius of that handle and compare it to the radius of the screwdriver shaft, and from there we could actually figure out what the mechanical advantage was of that screwdriver. This is why the thicker the screwdriver handle, the easier it is to turn. You maybe have even seen this with like jars and stuff and bottles, that when you have larger kind of tops to jars, they're easier than when you have smaller ones. I don't know. Anyways, all has to do with advantage. So the wheel does not have to be round. What is important is that the two turning objects are attached to each other at their centers, and one causes the other to turn. Wheel and axles, like levers, provide, of course, a mechanical advantage. Great example, steering wheel. So when I have a steering wheel, I've got this big, large wheel, which is where the effort is. And then from there, that goes to the steering column, right? Or like a thing that goes into the vehicle that then turns as a result, which would be your axle. So here's a question. With a steering wheel, is that giving us a force or a speed advantage? And the answer is it's a force advantage. The wheel is much bigger than the axle, okay? So when you think about it as a lever, this would be like we have a very large effort arm for a very small load, a load arm. Okay, so it's giving us a mechanical advantage way more than one, and as a result, it's a force advantage. Can also produce, though, a speed advantage with a different system when we have wheel and axle. So here's an example. You've got this really kind of funny bicycle. If you had a bicycle that just had the one gear and it was directly pedal to wheel, okay, when you think about it, you've got this small radius from here to the pedal. That does not show up at all, but you get the idea, compared to the large radius of the wheel itself. So for one rotation of the pedal, I get one rotation of this huge massive wheel, which is giving a speed advantage. But in this case, you'd have to apply more force to the pedal than the wheel would actually exert, that the wheel would give against the ground. So that would be a speed advantage type. So that's wheel and axles. That's our kind of basic thing. It all has to do with the radius of the two wheels in terms of what kind of advantage we have. And really, it's just the same as levers. We're just dealing with kind of a modified lever. So now, kind of just continuing on with the whole circular theme, we're also going to talk about gears today. Gears are wheel-like objects with teeth around its rim, and those teeth interact with other gear teeth in order to cause them to move. I can call two or more gears connected a gear train. A driving gear or a driver is a gear that force is applied to. And then a driven gear or a follower is a gear that spins because of contact to the driver. So the driver is kind of actually driving the thing. That's where the force is going to cause the other gears to move. And then the followers are moving because of the driver. If the driver wasn't there, they would not be turning. So here's a diagram showing you some drivers and followers. So here we've got the large one on the left is the driver in both scenarios. And then you can see that the rest of the gears are following because of the teeth interlocking and causing the rest to move. What do you notice about the movement of the different gears? So how does this one move in comparison to this one, number 2? And hopefully what you came up with is they're moving in opposite directions. This one is clockwise, it's going like this, and this one is going counterclockwise. And this is the case whenever we have gears connected like this, that the direction of rotation reverses with each gear. And here we're back to clockwise again, and then over here we're on counterclockwise. So every second gear is the same direction. Same thing here, got clockwise, this is counterclockwise, and then here again I have clockwise. So motion of gears, if connected through direct contact, the gears will move in opposite directions. So shown in that first diagram, let's take a look and do an example and see if we can figure out the direction of the gear movement. So here we have the yellow gear, the small one is our driver. So my first question here for you is, what direction will the red gear move? Will it be clockwise or counterclockwise? And the answer is that it's going to be counterclockwise. As this one moves down, it's going to cause these teeth to move down as well on this side. So it's going to go in this direction. Now, what about the blue gear? Is it going to be clockwise or counterclockwise? And the answer is it's going to be clockwise. It's going to go in this direction because as these teeth move up, the red ones, it's going to cause the blue ones to move up, so it's going to turn in the clockwise direction. Now, this whole system, do you think that this whole system is built to give a force or a speed advantage? And the answer is this is going to give a massive speed advantage. When you take a look, this small driver, massive force advantage. I feel bad, a force advantage. As I turn this once, this is going to move far less than once. It's going to go maybe, let's say, a third of the way with how many teeth there are. And when this goes a third of the way, this is only going to go fraction of that, let's say a tenth of the way in this direction. So one rotation here is going to give me only 1/10 of a rotation for the blue. So this is going to give me for sure an advantage on force, that more force will be exerted at this axle than was applied at this axle as it's going through. And that's because it has moved much less for the rotation. If gears are in a chain and sprocket connection, then the gears will rotate in the same direction. So maybe you've seen a system like this where we have like a bicycle chain going around 2 gears. And because this is moving, let's say clockwise, this one is also going to move clockwise as a result with this kind of connection. And where do you see this sort of gear setup? Well, I've already basically said it. You find it in bicycles, which have this kind of gear setup going, of course. So how do we tell the speed ratio between the 2 gears? How much one gear will move as opposed to another gear? Well, we take a look at the teeth of the 2 gears. So if I were to count the teeth of gear A and gear B, then I can figure out what the speed ratio is between the 2 of them. So here I have 1, 2, 3, 4, 5, 6, 7, 8, 9 teeth on gear A, and gear B has 1, 2, 3, 4, 5, 6, 7, 8, 9 teeth as well. This is a trick. So which gear will rotate faster or slower? Or will gear B rotate faster or slower? No, it's the same. It's the same. because they have the same amount of teeth. Both of them have 9 teeth, so they're going to move at the same speed. So the speed ratio between gears can be calculated just by taking the number of driver teeth and dividing it by the number of follower teeth, and then that will tell you how much faster the follower is going to go than the driver. So this tells you the ratio of speed increase between 2 gears. So this is when we have a smaller gear and a large gear. One place where we see this like crazy is in watches, where all these gears cause the second hand, like the actual seconds, to move at a different speed than the minute hand, which moves at a different speed than the hour hand. That all has to do with the amount of gear teeth that we have. And so actually you can know that the speed ratio with those is going to be 60 for, let's say, the minute hand, right? So one driver is going to, how do I put this? The speed ratio for the seconds, for the second hand going around, is going to be 60 compared to the minute hand. All right, so anyways, the size of the gear and the number of teeth each gear has will affect the speed ratio, and the relationship between the speed of rotations of a smaller gear and a larger gear, and we just calculated by taking the number of driver teeth and dividing it by follower. So driver divided by follower. So let's take a look at a few examples and see if we can figure it out. So calculate the speed ratio for a gear chain that has a driver gear with 25 teeth and a follower with 5 teeth. So I have a driver, it's 25, and I have a follower that has 5 teeth. So my speed ratio is equal to driver divided by follower. So I have 25 divided by 5, which is just going to be equal to 5. So at the end of the day, this means that the follower is moving 5 times faster than the driver. Calculate the speed ratio for a gear chain that has a driver gear with 6 teeth and a follower gear with 36 teeth. What do you think the answer is? So I have a driver that has 6 teeth, and I have a follower that has 36 teeth, and I want to know what is the speed ratio. So speed ratio is equal to driver over follower. So I have 6 over 36, which means that I have 1/6 when I actually lower that down. So at the end of the day, the speed ratio is 1/6, which means the follower is moving 1/6 as fast as the driver. Compare that to here, where I had way more teeth for the driver than the follower. Well, here it's the opposite. Here I have way more teeth for the follower than the driver. So this is 1/6 as fast for the follower than the driver. Last thing we're going to talk about today, now that we've talked about gears, is pulleys. Pulleys are grooved wheels with a rope or chain running along the groove. So here's a picture of a pulley. It's again similar to a class 1 lever, except that instead of actually having like a rod or something, we have a rope. So it's like a flexible lever, and the axle acts as a fulcrum. Each side of the rope are the effort and the load arms. Now, a big difference here is that because it moves and it's not stiff, we don't have like a bar, that wherever I have rope, the tension all throughout the rope is going to be the same. So if I'm applying 50 newtons of force to the rope here, pulling it, then that means that over here, the rope is going to have 50 newtons of force as well. So fixed pulley is where I have a grooved wheel that's attached to something that doesn't move. So if this was attached to the ceiling or something, that would be called a fixed pulley. While a movable pulley is attached to something that moves. So a movable pulley itself actually moves. With a fixed pulley, the position of this pulley stays the same the whole time. With a movable pulley, that's not the case. This pulley will actually move up and down. So there would be another pulley over here or something that then as we pull the rope, it would bring this up. So with pulleys, we can actually cause it to have like force or speed advantages. We can kind of like do some stuff in order for us to have less force applied to the rope than applies to the load, and by doing some fancy things with the rope. With a single fixed pulley though, it's really simple. We're not dealing with changing the force or anything. A single fixed pulley is only meant to change the direction. So instead of here having to pull up, this allows us to pull down and lift something up in the meantime. So this would make it a lot easier to lift something up from the ground, right? By using this kind of a system, just by changing the direction that the effort or force is. So a single fixed pulley does not change the force at all. It just changes the direction. Now a compound pulley, like a block and tackle, this is actually meant to change the force. So in this kind of scenario, I can change how much effort or force is needed in order to lift something up. And the way it works is that all of these ropes are supplying 25 newtons to pull up this 100 Newton weight. So every one of these pieces of rope has the same tension and it's all connected. So I'm lifting up this 100 newtons with 25 plus 25 plus 25 plus 25, which means I'm pulling it up with 100 newtons. But I'm doing that by only applying 25 newtons to the rope. But because the tension is the same throughout the whole rope, all of these add together. So I add together all of the ropes between the weight and the top. Okay, so I got 1, 2, 3, 4 ropes. So 4 times 25 gives me 100. So a block and tackle, or a compound pulley, is composed of a number of fixed and movable pulleys. More pulleys usually means a greater mechanical advantage, so that less force is required. This could keep on going back and forth and back and forth. What's interesting though is because the force required to pull this is a quarter of the force, that also means that I have to move it 4 times as much. So if I were to pull down and move this, let's say 4 meters, this would only move up 1 meter. So this is again, the whole idea of the work is going to be the same, which is the force times the distance. So if I have a quarter of the force, then that means I need 4 times the distance in order to get the same work done. So the mechanical advantage of pulleys can be found by counting the number of ropes between the load and the top pulley in these compound pulley type problems. So here's some kind of pictures to go through this. I actually want to skip past this slide to look through the individual slides. So this is my simple type of single fixed pulley, where all it's doing is changing the direction of the force. So it's 100 newtons here and 100 newtons here. And if I move this down 10 centimeters, this lifts up 10 centimeters. I'm not getting any mechanical advantage here. It is simply 1. It is the same as if I just lifted it. But here now I actually have a compound pulley system where it goes from here to a movable pulley and then up to a fixed pulley. But as I pull this rope, these 2 ropes end up pulling up on the weight. So each one of these ropes pulls up with 50 newtons to lift the 100 newtons. So I only have to apply 50 newtons of force in order for this to happen. In other words, this gives me a mechanical advantage of 1 because I have 2 ropes between the weight, the load, and the pulley, the top pulley. So 2 ropes. Here I have a mechanical advantage of 3. Because I have 1, 2, 3 ropes. So because I have 3 ropes that are between the load and the top pulley, I have a mechanical advantage of 3. So if I were to pull with, let's say 10 newtons on this rope, I'd be applying 30 newtons of force to this load. Continuing on with the 100 Newton load here, then that means that in order for us to lift this 100 Newton load, I only have to pull with, this number is wrong, but 33 1/3 newtons of force. And if I pulled 30 centimeters down, it would lift up this weight 10 centimeters. Again, the work is the same. Okay, here's another one. What's the mechanical advantage for this? And the answer would be 4, because I have 1, 2, 3, 4 ropes between the load and the top pulley. So in this kind of scenario, if I were to lift the mass up 10 centimeters, and that means that I would have to lift this rope down or pull it down 40 centimeters in order for that to happen. In order for me to apply 100 newtons of force on this load, I would need to pull with 25 newtons of force here. Okay, so every single one of these ropes would have 25 newtons of force, because again, throughout the rope, the tension is the same, 25 newtons. Okay, really what this comes down to is again the same kind of idea of mechanical advantage is equal to load force divided by effort force. So here we have the load force of 100 newtons and here's the effort force of 25 newtons. This is our lever formula for mechanical advantage, but this allows us to kind of solve for some stuff. So if you're missing a load force or an effort force, you could figure it out just by knowing the mechanical advantage of the pulley system. And we can find that by counting the number of ropes that are between the load and the top pulley. I'm not going to have you do that, maybe on a worksheet or something, not on a test. But really important just so you understand that the more ropes I have in my compound pulley system, the greater the mechanical advantage I have. So as this goes, starting here, 1, 2, 3, 4 ropes, 4 lines between my load and the top pulley, I get 4 times the force that I apply at the end of the rope that applies to the load. So kind of neat. I really like pulley systems. I think they're fascinating. It's cool stuff. All right, so that's it for today. What do you have to learn? What do you need to know from all this? Well, we started out by talking about wheel and axles and understanding the wheel and axle is really just a lever, right? Just kind of a different lever, and that we can look at it as the load arm and the effort arm for the wheel and the axle. You learned how to kind of do some calculations around mechanical advantage and speed advantage based on that. So realizing how that works. Then we went to gears. You need to know that when gears touch in a gear train, that each second gear goes the opposite direction. So the direction changes with each gear. You should understand how to calculate the speed ratio from the number of teeth for that. And then finally, we learned a little bit about pulleys and figured out how to figure out the mechanical advantage for pulleys and learned some terminology like fixed pulley and movable pulley and that sort of stuff. Okay, that's it for today. Have a good one.